Morning, everybody. Hopefully you guys aren't having any trouble connecting. I think for the most part, I think for now, we'll keep using that Zoom link from last time that I shared with you. If that changes, and it likely will, I'll update everybody in class, all right? So hopefully you guys all got the most recent message on how to log in, and it seems like most of you are getting in. So there's a few little updates that I wanted to give. But everybody can hear me okay? Can you guys nod, the ones that are on the screen? All right, thank you very much. So in terms of the registering for the Pearson online homework and all that stuff, they're making progress. They said within the next couple hours, I'll have the instructions for your individual course, so you can get in there and follow the links and get your access. I'll be assigning the homework for chapter 1, hopefully sometime today, and I will make it due next Wednesday, Wednesday evening. So that's just, in terms of Pearson, that's the update right now. So be on the lookout for a message from me with some instructions for you to get that set up. I guess the other thing that I'll say is, for those of you that maybe cannot purchase the online access at the moment, you can still get in there and set up your account. And in that case, they give you, I think it's a 2-week trial period. So you should be able to get in there, start doing your homework already. It gives you a little bit of time so you can go in and pay for it. And the other issues with so some of you will be getting the online access by buying an access code from the bookstore. And I'll make sure that I double check you have the correct ISBN number for that. Because the main thing is that, and I think I shared this in the previous instruction, is you just have to make sure that access code is for, so it's going to say something like Pearson 4th edition, etc. But you need to make sure it starts with the word modified. And the word modified means that it's just going to make it easier to link up your account with Blackboard to make it a little bit more seamless. So just make sure that it's a modified, mastering physics account. If for some reason they don't have any, I think it may not be the end of the world. You can still kind of get it, and we can kind of call the reps and they can, link your account manually. But it's best if it's just a modified account. All right. The other announcement I wanted to make has to do with attendance. So this week, I won't be taking attendance just because people are still kind of getting in the groove of things. But I'll let you know when we officially start taking attendance and what to do if you can't make it to the live meeting, what option you have there. So don't freak out about it. If you're here now, great. And if you're watching this as a recording, don't freak out. There's no assignment for that you have to do to prove participation for this week. So just wanted to put you at ease about that. So I got a message. Okay, so all right, Skelton, I just got your email, but it looks like you're here, so we're all good. Yeah,
I just in the waiting room forever, so I was like, I don't know if I'm in the right spot.
Yeah, no, you're fine. It's just this is one of the modifications I have to make sure that the default is set to disable the waiting room. But I think yeah, we're good now. So hopefully, yeah. So that's the issue with the attendance. I'm not taking it this week. Don't freak out. So today we'll be continuing chapter 1. One of the things that I did want to make sure everybody's aware of, I sent a message last week letting you know that the new lecture slides for the current edition of the book are posted online now. So you should be able to go into the homepage, and if you click the same lecture slides link, you'll now see that there's a new item that has all of the night 4th edition lecture slides. So I recommend you just download those so you have them a local copy on your computer. For today, I'll still be going through the third edition lecture slides. They're almost identical. And my goal is that we'll finish chapter 1 today. So, and I still, on my list of things to do, I will be sharing my OneNote notes at some point, but still, you should still be taking your own notes. And finally, and I'll try to remind you of this at the end of lecture, there is a mini assignment I have for you guys for next meeting, and that is on the new set of slides and on chapter 2. And let me go ahead and just share my screen already so I can start writing that stuff down for you guys. Here we go. Okay, so hopefully you guys can see my screen right now. So as I mentioned, I have a mini assignment for you guys. So by next class, Wednesday, which is the 2nd, it's just a matter of just watching a short video. And that short video is on the chapter 2 slides. Sorry. My mouse is being a little slow. So chapter 2 slides, slide number 22 has a video link. And it's just a quick summary of what that chapter is about, just to kind of get your head thinking in the right way. And so this is the 4th edition slides that are posted on Blackboard. And I might just send you a direct link of that to lower the effort barrier. But for now, make sure you go open those slides and click on the link, take a look. I think it's worth, it's just like a 4-minute video, that's all. All right, so we're gonna go ahead and begin now. Last time we talked about, we left off at significant figures and scientific notation, and that was all I'm gonna discuss in that sense. I might mention it briefly every once in a while. And so far, as a little bit of a review, we've talked about, I'm gonna disable these buttons on my cursor, on my, sorry. Okay, I don't know what it's doing. All right, so we've discussed properties like displacement, and we said displacement, we can call it D, or we can call it delta X. Delta X is defined as the difference in 2 positions, so the final minus the initial position. Other important quantities that we will be using today is velocity. And we mentioned that, so in this case, the velocity, V, is equal to your change or your displacement, which is your change in position over a time interval. So we'll be using that today. So displacement over time interval. In terms of units, displacement has units of length, and we're going to use meters as our SI unit. And for velocity, the units are what's distance over time, or we use units of meters per second. I'll just spell it out just to make it clear that that's what we're talking about. The abbreviation is lowercase m and s, right? So the next topic, we've talked about motion diagrams, and our idea now is to introduce a concept known as vectors to represent motion. And so we've, in a way, indirectly mentioned Scalar quantities are quantities that only have a magnitude, and vector quantities have a magnitude or a size, and they tell you the direction. So in terms of a few examples here, so let's say we got scalars and vectors. Well, if I were to ask, well, what's an example of a scalar? Put the word examples here. Well, earlier we talked about distance. Distance is a scalar. It tells you about how far something is. But the corresponding vector quantity is displacement, because displacement doesn't only have a size, but it also tells you what way. So if it's a change in position, it's not good enough to say it's 10 meters or 11 or 12 meters, but we need to say whether you went to the left or to the right, east, west, etc. In terms of, and we did the same thing with speed and velocity. If we mention, so if we touch on speed, speed does tell you how fast you're going or how slow you're going, but it doesn't tell you which way. But velocity is a quantity that does tell you not only how fast you're going, but what way you're going. And so those are critical differences between scalars and vector. So scalars only have magnitude or size, and a vector is going to have both magnitude and direction. All right, so those are the main differences. And because a vector has a magnitude and a direction, and actually the word vector is related to like the word arrow, we're going to represent vectors using arrows. And we'll do some examples in a little bit. And the idea here is that the size of the arrow is going to tell us about magnitude. And the direction of the arrow is going to tell us about the direction of the quantity, or that thing that we're discussing, that physical quantity. So if we go back to our cartoon of Jane, and now we've got Sam at these on the street. We're looking at this top view of a map, and so you see Jane has this displacement vector that goes from the bottom of the intersection to the other street on Vine Street. And so we label her displacements as D, the subscript J for Jane. We look at Sam's displacement, and so he's got a label with a D and a subscript S for Sam. And one thing that's interesting is if you look at the arrows, well, we can say they look about the same size, the same length arrows. So those probably have the same magnitude. However, they're not the same displacement, because one of them is pointing diagonally, to the top, and the other one is pointing horizontally. So in this case, those are actually two different vectors, two different displacement vectors. And it's important to know and so it might matter that Jane's vector is pointing upwards, right? I mean, you're gonna end up in a different spot. And so this kind of highlights why we have to emphasize that there's a direction that goes with these displacements. It's not just the size of the arrow. So it turns out that you can add displacement vectors, just like you can add other quantities. Even though these things have a direction, there's a way of adding them. And the first method we're going to learn about is called the tip to tail method. So make a new tab here, and we'll call this vector displacement. or I'm sorry, vector addition. And so the first method I'm going to discuss is this tip to tail method. And so the first question is, well, what do you mean by that? Well, if we had, for example, a little vector, we'll call this vector A. Now, one thing that you'll notice is we'll put a little symbol on top of the arrow of the identifier. Sometimes you'll see an arrow drawn like a proper arrow, kind of like what I just did. Or because we like to be quick and a little lazy, sometimes I'll just make it like that. But it means the same thing. It means it's anytime you see that little arrow symbol over your letter, it means we're dealing with vectors. And so in a vector A like this one, there's going to be parts to it. In this case, the bottom part here, that's going to be the tail of the vector. And where we have the arrow tip, that's going to be, if I can get this to cooperate, that's going to be the head of that vector. And so if we do this example here, to add vector A plus vector B, well, first of all, I need to tell you what those look like. So in this example, vector A looks like that, and then vector B is kind of pointing downward. I'm just following what's in the slide here to the right. So tip to tail method means that you're going to take A, and one nice thing about vectors is that you can translate them over. So what I just did to move it there is I just translate it. Basically, this is just another way of saying I drew it again, right? So basically, I copied and dragged the vector over. So I say drag because that's kind of what we do with our mouse, right? Anytime you click on a picture and you drag it around on the screen, you're not rotating it, you're not changing the size of the arrow, you're just copying it or just dragging it to a new location. Okay, so translating a vector is the same thing as like dragging a vector to a different place. That's what I just did there. And we're going to do the same thing with B. And so the trick now is to say, okay, well, tip to tail method means you're going to take the tip of A and you're going to attach to the tail of B. So you're going to take B and we're going to stick it right there. And I guess I could have actually dragged it with my actual mouse, but basically that's what we're doing. So you take the tip of A, tail of B, and then the answer is going to be where the place, basically is going to connect the start to the finish. So what does that mean? Well, that means in this example, we started with A, right? So this point right here was the start. And the tip of B, that's where we finished. And so start to finish, that means that we're going to make a new vector that connects the beginning point to the ending point. So this arrow here, that's basically our answer. So we can call this a vector C, where C is the answer. So in this case, A plus B equals a new vector called C, which I just drew on the screen here. And so that's kind of all there is to it is, when you do tip to tail method, you take the first one, put it there, take the next one and attach the tail of that second vector to the head of the first one, all right? So if we go back, so here's our picture of Jane and Sam. And in this case, I guess the important thing to emphasize is these displacement vectors don't necessarily care about what's in between the starting point and the end point, right? So if I were to draw that picture that we have on the slide here, Well, even though maybe Jane started here, so we can put, we'll use a D for displacement. So D initial for Jane was down there. And then she ended up somewhere else on this other street here. And so that's the D final for Jane. Well, if you remember displacement, you know, if we use a D in this case, it's going to be the final minus the initial. Well, in essence, what you can do in that case is you can just connect the initial to the final point, and that's going to be Jane's displacement. So we'll call it dj, which is the total change. Now, you could go through this whole step that I did, the a plus b equals c, if you end up choosing a reference point. So you can decide, well, if you make the starting point be 0, 0, then the first displacement is just a 0 vector. The second displacement is just the one that connects the beginning to the end, and then you get the answer. There's more complicated ways of doing it. You could have chosen to make the center right here and then drawn some arrows from here to the beginning. But maybe that's, you know, I don't want to muddle things. So let's kind of, I guess, move on here. So, but the main point is that wherever you start off, so in this case, if we're looking at Sam, we have the initial position of Sam, the final position of Sam. Well, the displacement is just the arrow that connects the initial to the final point. So this would be the displacement of Sam, and we put a little arrow to remind us that it's a vector. All right, so I think I kind of had gone the wrong way, but let's do one of these quick check problems. I didn't ask you guys to log in, but please log into your Reef account if you haven't done so already. I've actually got it going this time. So everybody's logging in. And like I said, if you aren't able to log in fast enough for this one question, don't worry about it. There will be more. But in this case, let's go ahead and do, actually, right now that I just clicked, are you guys seeing the wrong screen? Okay, so let me stop this. So let me start it again. So hopefully now you see the right screen. Is that correct? Nod, please. All right, cool. So in this quick check, they're asking, given vectors P and Q, what is P plus Q? So using the tip to tail method, our goal is to figure out whether the answer is A, B, C, or D. So far, I've got a few A's answering here. But let's, so while you guys kind of draw it out and try to figure it out, I always recommend that you do, in fact, draw it. It's hard to kind of figure these out sometimes if you are only thinking or looking at it. So our goal, so this is quick check 1.6. We have P, looks like that. We have Q, that's kind of is horizontal, not like what I just drew. And so the idea is to do P plus Q. So P plus Q, if we use tip to tail method, we're going to start with P. So here it is. That's the starting point. And then that's the tip of P. And then Q, using tip to tail method, we're going to take the tip of P and put on the tail of Q. So it's going to go, I don't know why it's doing that, kind of like that. So that'll be Q. That's P. And so we started here. We ended here. So then the answer, as some of you correctly have answered already, is going to be the arrow that connects the start point to the end point. So it'll be something that looks like that. All right. So if we go to the next slide, sure enough, we see that's how it worked out. All right. Okay. Let's see if we can try another one. If you guys have questions, just ask. I know there's also this option to like ask a question by raising your hand sometimes, but if you just want to ask something, just unmute yourself and ask, because I'm not looking at chat messages or anything like right now. So don't be afraid to just interrupt me.
Can you please re-explain how that works?
Okay, so in general, the addition of vectors.
Yes.
So the idea, and so I have it on this slide, but let's just make one more slide here, start from beginning. So the idea here is the tip to tail method of vector addition. Okay. So we're going to take, in the previous example, we said, so they want us to figure out, the goal here is to find the vector produced by adding the following: P, vector P plus vector Q, all right? And so they told us P is a vector, kind of looks like that. They told us Q is a vector that looks like this. And so in this technique of tip to tail method, we can take vector P, and you can just, it's basically like a copy and paste kind of thing, where you take it and then you drag it over somewhere else out here, like where we're gonna do the calculation. And then when you label the parts, you know, like I said earlier, this is always gonna be the tail end of one, that's gonna be the tip. Similarly, vector Q has also a tail and the tip. And so in tip to tail method, you're gonna take the tip of P, is basically what it means in this case, is tip of P with the tail of Q. So in that case, you're gonna take Q that I've drawn right there, I'm gonna select it, and then I'm gonna grab it and just move it over. If I can actually, there we go. So you're gonna take Q, so you see the tail of Q, we're gonna put it right on the tip of P, kind of like that. And I'll put a little bit offset just so we can read both letters. But that's basically what you're doing. You're connecting those two in that manner. And then the answer is going to be where you started off. Let me get a slightly thicker marker here. The answer is going to be the starting point. In this case, the starting point was the tail of P. And then the end, and so it's going to be an arrow that connects the starting point to the end point, which is the tip of Q. So in that case, when you look at your cartoon there, well, we're gonna connect it in that way, where we say, okay, well, we started here, and then we're gonna end at the tip of Q. So your answer is this arrow that I've just drawn in blue. Does that kind of make a little bit of sense? So that's the answer arrow. And so in that example that I gave, that's why we kind of picked the one that was pointing down and to the left a little bit. That's the only one that results when we do the addition this way. And that's the correct way to do the addition. So, I mean, so it's, thank you for asking it, because it's, even though for a lot of you it might seem like pretty straightforward and obvious, you're gonna be doing a lot of this vector addition, and later on it's gonna get even a little bit more complicated. So these are kind of basics that you have to make sure you understand. Okay, so that's in general the method. Now, at the same time, we do get to make use of other properties like Pythagorean theorem. So let's look at this example here. So on the slide right now, we have example 1.7. This is on slide 70. It says Anna walks 90 meters due east and then 50 meters due north. What is her displacement from her starting point? And so in this problem, you know, they're telling you directions east and north of some place, and that place is her starting point. So let's write down the information here. So Anna walks 90 meters east. And then Anna walks 50 meters north. This, when you think about this, you should imagine that this is like two vectors that you can draw. And in this case, the reference is going to be her starting point. And in this case, we can make this the coordinate, X and Y is equal to basically 0, 0. So we can make a nice little coordinate axis like that. We can say, okay, she started right here. And if we try to map on those directions, then the first thing says that she walked 90 meters east, right? So from that starting point, well, we have to decide, right? We have to make a definition of what's north, east, and west. So in this example, I'm gonna make north be up, south is down, west is to the left, east is to the right. So here, because she walks 90 meters east, we're gonna draw an arrow that goes some amount that is supposed to be 90 meters to the east. And then it says she's gonna walk 50 meters north. So that's gonna be another arrow. So from the tip of the first arrow, we're gonna start a new vector that goes northward. Anyway, I like that. So then this vector has a distance of 50 meters and it's pointing upward and north. And so in order to get her displacement, well, we started off here and we ended up at the tip of that 50-meter arrow. And so the displacement then is going to be the arrow that connects where you started to where you ended. So this is going to be her displacement. And the nice thing about this is because east and north are perpendicular, that means we have a nice 90-degree angle here. And so from this point, in this question, they're asking what's her displacement from the starting point. So the goal is to find what is the displacement. And remember, there's two parts to it, right? One of them is magnitude, and one of them is direction. So in this problem, to get magnitude, the easiest thing might be to use Pythagorean theorem. So in that case, we have basically a nice right triangle, 90 on one side, 50 on the other. And if this is side C, then we know that C is equal to square root of 90 squared plus 50 squared. Everybody following? Does that make sense? And so in this case, if you punch into a calculator, you'll get an answer out. And so I'll let one of you guys type it out and let me know once you have it. At the same time, that'll give us the magnitude, but to get the direction, well, we know that there's we know at the end it's going to be some kind of northeast direction, right? But we need to know the angle. What is this angle theta? And I haven't written it down here, but in these kinds of questions, you're going to want to always put, okay, we'll say, well, I need to know how much north is she actually going, to quantify it better. So we need to know this angle. And so in that case, here the question is, how do we find out that angle? There's a few options, but using the information we know already, we could use the tangent function. So tangent of theta, which is opposite over adjacent. Well, that's going to be given by, so the opposite to that angle is going to be the 50 meters. So this opposite is 50. And this side right here, the adjacent, is equal to 90. So we're going to have the tangent of theta is equal to 50 over 90. Okay. So real quick, did anybody calculate the length of side C or that displacement? No. You gonna make me do it? Somebody must have done it. I'm sure one of you guys has a calculator.
I got 102.95.
Okay. So you got 102.95. Anybody disagree with that? So 102.95, and we can round that up to 103. All right, and that makes sense. It's got to be a little bit longer than the corresponding sides because it's the hypotenuse, so I'm not going to argue it. The next part is to get the angle. So if we have tangent of theta is equal to 50 over 90, which is the same thing as 5/9, we have then tangent of theta is equal to 5 over 9. So theta is going to be given by the inverse tangent. Hopefully you guys remember that. Inverse tangent of 5 over 9. And if you have your calculator set to degree mode, you'll get an angle in degrees. Anybody have a number for that? I'm guessing it'll be kind of low, maybe like 15.
I got 0.50.
Okay, so you get 0.5. So do you know if that's in radians or in degrees?
Degrees.
I think that might be radians because I got 29
Oh.
degrees.
What was the answer you got? 29 what?
29 degrees?
Ah. So yeah, it is correct that the first 0.5 is probably in radians. So one way to know that, well, first of all, there's a little button that you can click to switch between radians and degrees. But just as a quick kind of a way to try to remember this, whenever you're in radians, you're going from 0, a full circle is going to be 2 pi. So that means half a circle is pi. A quarter of a circle is pi over 2. And whenever you get units in radians, that's telling you the fraction of this number. So if pi is equal to 3.14, this number is like 1.5 something. Then a number that's down here, so 1.5, if you divide that by 3, you're going to have basically something that looks like that, where this thing is like a third of that 1.5, and then that's 1. And a third of this right here is about 30 degrees. So probably that 29, it's probably more, it depends on what numbers you use to do a tangent. If you use exactly 5 and 9, then I am curious because 0.5 should be exactly 30. Any other person wants to chime in there? So I guess the only lesson here is 0.5 was an answer in radians. The 29 was an answer in degrees, but they're both correct answers. But you'll notice that in the example here on the slides, so the first part is, and this is where I think the discrepancy comes from our choice of significant figures, right? Because I made the assumption like, okay, well, I rounded it to 103, which is, it's a one way of rounding up 102.95. But then if we look at significant figures, right? I mean, really, the number 90 and the number 50 have basically one significant figure. So really, if you round it to 100, that's going to give you a slightly different number. And I think that's why we have a discrepancy. Maybe. At least with the magnitude, that's, so we got a number that's pretty much the right answer. And when you look at the next slides here, so when they calculated theta, we did inverse tangent of 5 over 9 gives you 29. So we got an angle of 29. The next question is, well, how do you report this? You can't just say 100 meters and then 29 degrees. People need to know, well, what direction, right? So the correct way of stating this answer, and I'll just put a big arrow going up here, is going to be that the displacement is going to be 100 meters And so it's gonna be 29 degrees north of east. So this weird, so, and we don't, I mean, at least when I walk around, I don't hear too many people talk this way, but this word that's north of east, of is another way of saying like with respect to. So with respect to east, we went 29 degrees north-ish, right? Because you could say 29 degrees south of east, and in that way, in that case, our arrow would be pointing like down and to the right, okay? All right, so, oh, that's why I keep pushing the wrong arrow, sorry. So hopefully once you, you know, if you had drawn the triangles to a correct scale, you would get an idea that, yeah, the angle must be kind of like around 30. It can't be too big. And actually, I mean, so for example, 90 is roughly twice the size of 50, right? So if I had drawn it correctly, 90 would have been like this, and then 50 would be like not quite as long, maybe like that long. And then, so when you draw it that way, then okay, you can say, well, yeah, that sort of looks like a small angle. The way I drew it initially suggested the angle was maybe a little bit bigger. All right. So this is how we do math. That was how we did math with displacement and displacement vectors. We're gonna focus a little bit more on velocity vectors next. And it's the same idea. We're gonna point the vector in the direction of the motion. And with a velocity vector, the magnitude is gonna tell us about the size or the magnitude of the, so the size of the arrow will tell us the magnitude of the velocity. So, that's not what I meant to do, sorry. So let's kind of, sorry about that. Okay, so similarly, and one of the things that the book does a really good job of they do a good job at color coding everything. So in the book, you'll notice that they have this convention where displacement arrows, I'll put the arrows here. For displacement, they're usually going to be blue. And if we're talking about velocity, they're usually going to draw them green. And you'll see as we introduce other kinds of vectors, we'll see other color arrows. But the idea here is if you've got a displacement vector, like they have in that picture, and as time goes on, the displacement gets bigger and bigger, that's because we're covering more distance every second. Well, that also implies that we're speeding up, so your corresponding velocity vectors will also be slowly increasing as time goes on, all right? But we do it the same way. We point them in the direction of that quantity. And we're gonna end up drawing velocity vectors in 2 dimensions as well. So in this case, they show this ball that got thrown at a 60-degree angle. And so initially it's going pretty fast as it goes upward into the sky and gets ready to start coming back down. You can see that there's the size of the arrows kind of decreases a little bit. And then as it starts heading down again, it starts to speed up again until it reaches its maximum speed right before it hits the ground. And one of the things that you'll notice in this drawing is that there's a symmetry to it, right? The arrow at the beginning is the same size as the arrow at the end. They're just pointing in opposite directions. And this is actually a realistic representation if we assume that there's no air resistance. So if it's windy, you know, if the wind can slow the ball down, then that won't be true. But in this case, we're assuming it's not windy. There's no friction from the air. And so you get this nice symmetric figure for the trajectory of the ball. So what we're gonna do now is, so just kind of a little bit of a summary of the things that I've talked about so far. And in general, for the following chapters, you're always gonna have this format where the beginning of the lecture slides, kind of ask you to, well, they'll tell you about the big ideas we're going to cover. And there's going to be a little bit of a review sometime. And there's at the end of each chapter, there's also going to be a very well-developed summary of everything we talked about. And one of the things that you'll find is I'm not going to spend too much time going over those preview slides. And I'm also not going to spend a whole lot of time going over the summary slides at the end of the talks. And so I'm asking you guys to spend your own time going through those. And really, when exams start to get close, I will give you a review, but I'll also tell you to look at those summary chapters because, or the summary slides at the end of each presentation. They do a good job at just wrapping everything up. They let you know what are the really important things you need to know, okay? But like I said, I'm not gonna cover them or spend too much time in class going over them. So let's do another example. This one's gonna be a little bit more involved. And so in this case, the title of this example is called A Goose Gets Its Bearings. And the idea here is we're gonna follow a goose and try to answer the questions that were asked. So let's draw it first. It says here, figure 128 shows the path of a Canada goose that flew in a straight line for some time before making a corrective right angle turn. And then it says after 1 hour after beginning, the goose made a rest stop on a lake due east of its original position. So like I said, even though it's drawn out there for you, I always recommend you still draw your own picture of the problem. So it says here, he's going to fly so just because he flew in a straight line doesn't mean he has to fly horizontally, right? It just means it's a straight arrow. And on the picture, they tell us that that distance was 21 miles. And then it says after that time, it just says after some time, it made a corrective right angle turn. So it made a nice right angle turn. So this angle here is what they're talking about. So this corrective turn is basically him going like, oh crap. Because there was probably like a watering hole or something out here, right? Yeah, there's a lake. So he really wanted to get to Little Lake to drink some water. So he was going the wrong way out here. And I'm sure everybody's had that experience of going the wrong way. And after he took that turn, he traveled 28 miles to get to that lake. In this particular problem, we have decided to make the upward direction be north. And so they want to know after an hour. So after an hour, it actually landed, right? So start was here. The lake was the finish line. And this entire trip took 1 hour. So entire trip, 1 hour, all right? So there's a few questions that they're asking us here. First one is, how much extra distance did he travel due to the initial error in the flight direction? So in other words, how much farther did it fly than if it had simply flown directly to its final position on the lake? So the arrows are the actual path. What it should have done is it should have just kind of gone from the start point all the way to the finish line right here, right? This is like the ideal path. So they want to know how much farther did you go? So basically, if we say total trip was, what was it? 21 miles plus 28 miles. Add that up, that gives you 49 miles is the actual trip. In this case, they want to know how much farther did he fly? Well, we need to know in that case, what's the ideal path? So let's make, I'll make a little vector called d ideal. And so the answer in this case is how much farther is going. The answer is going to be 49 miles minus whatever was the ideal path is going to give us the answer in that case. So we need to know what is that hypotenuse of this triangle, right? Because it's a right triangle. And so in this case, the ideal path is, we can use Pythagorean theorem. So d ideal is going to be d ideal squared is equal to 21 squared plus 28 squared. So that this magnitude, so this is to calculate the magnitude of that displacement. D ideal is going to be the square root of 21 squared plus 28 squared. Okay. So what might be the answer? Anybody want to do it? I could try to do it here, but. So you do 21 squared plus 28 squared. It's going to give us this number, 1225. We could take all that, put it in parentheses, and there's a thing, so here's a square root, is SQRT, I think. So square root of 21 squared plus 28 squared is going to give you 35. All right. So here, it's the square root of 1225, which is 35 miles. So that's the ideal, path. So then the answer is going to be 49 minus 35 is going to be what? 14 miles extra is what he traveled, okay? Any questions about that? All right, well, so that was part A. Now part B is going to be, what is the flight speed of the goose? So flight speed, in this case, it's going to be the total distance over the time. So the total distance we already calculated before was 49 miles, right? So we're talking about 49 miles. And what was the time that it took for that to happen? So if you remember the problem at the beginning, it says the entire trip took 1 hour to get to the lake. So in this case, the speed was just 49 miles in 1 hour. It was just 49 miles per hour, okay? And it turns out if you calculate that and turn it into kilometers, it's similar to about 80 kilometers per hour. And if you remember, apparently that's a good speed for a goose. Which I guess makes sense, right? I mean, a lot of times you see, if you've ever seen a bird flying, right? I mean, and a goose is just a slightly bigger bird. You'll see, they kind of fly about as fast as a car, and 50 miles an hour is kind of an average speed for a lot of vehicles. The reason that it's good to check this is you don't want to get an answer like 2 miles an hour, because then you're like, nah, I don't know, that's a little too slow. I walk faster than that, right? Or if the answer is like 300 miles an hour, you're like, yeah, that's kind of like the speed of an airplane. So I'm not sure about that either, But a number in between means that you didn't screw up too badly, right? It would have been bad if we had gotten a number that was like 1,000, right? So it's good to check yourself before you move on. All right, so this kind of shows the process. This is what we did. We got 35 miles, total distance 49, etc. And yeah, so you can look at those for a little bit of extra discussion, but I think we covered all those topics. And so this chapter is pretty much, that's the main concepts that we're covering in chapter 1. We went over motion diagrams. This is the part that I'm telling you, you can kind of spend some time on your own reviewing, or either now or when you prepare for an exam, or or when you're trying to do the homework, right? If you're like, man, I don't know how to approach this, how to begin, just go through these slides a little bit. They start off with motion diagrams. They go on with to scalars and vectors. They go from the motion diagrams to putting them on a number line. And they go through, just explaining things we talked about, like how do you get displacement? How do you define velocity? They go over units a little bit. How do we do conversions from scientific notation if we're dealing with big numbers or little numbers? We also talked about significant figures and how to handle it when you're doing multiplication and division, and how to do it when you're doing addition and subtraction. So that's kind of all there is for this chapter. And I was gonna maybe start chapter 2, but like I said, maybe go watch that video and we'll start chapter 2 using the new slides next time. Usually I'm gonna try to end our lectures about 10:10, just to give me a little bit of time to prepare for my next class that's hybrid, so I have to walk somewhere else. But I think for today, that's all I have. You guys have any questions? So as I mentioned, I'll send you guys an email today with the instructions on registering for Pearson. That should be ready anytime or pretty soon, all right? And I'll hand out the assignment and you guys can ask questions if you got them at that point then, okay?
As of right now, there's no assignment until we get that link, correct?
Correct, yeah, there's currently no assignments. Once I post the assignment, you'll know about it. I'll send the Blackboard update. And like I said, when I do assign it, it's gonna be due next Wednesday, the 9th of September, okay? All right, well, if there's no more questions, then I guess we'll end here, guys.
For the book, do you have the link of where we could buy it from Pearson?
So that's the information that I'm gonna send out shortly once I get the activated links from Pearson. So like I said, they're working on them, and if I don't have the email already saying it's ready, I should be getting it soon, and I'll share it with you once I have it. And that'll give you instructions on registering through Blackboard, which is the recommended way. So yeah, you should get that today, right? All right, guys. Well, if there's any questions, just shoot me an email. Let me know if you need to discuss anything. All right. And if there's no more, then hope you guys have a great day. And I'll make sure I put the recording on a lot faster this time around since things are set up now. All right. Okay. Well, you have a good day. Bye-bye.